Hello all, I'm Jaya Sreevalsan-Nair presenting the work done with Pragyan Mohapatra on the influence of aleatoric uncertainty on semantic classification of airborne LiDAR point clouds, supported by a case study with random forest classifier using multiscale features. Semantic classification, that is the object-wise classification implemented on three-dimensional points in a point cloud, needs feature vectors for supervised classification. Given these are environmental data sets, it is expected that the data has inherent uncertainty. We know that the uncertainty influences the classification outcomes. We pose the questions of how does the uncertainty in the data or the feature extraction manifest itself in the classification outcomes, and how can we measure the same? Aleatoric uncertainty corresponds to the uncertainty present in the data, while epistemic uncertainty corresponds to that in the learning model. There are two sources of aleatoric uncertainty: task-dependent or homoscedastic uncertainty and data-dependent or heteroscedastic uncertainty. Task-dependent uncertainty arises from feature extraction computation. We compute the likelihood of a point belonging to a surface type, line type, or point type features and represent them as a saliency map. Here we show the barycentric coordinate representation of the saliency map. The Shannon entropy computed from the saliency map gives the task-dependent uncertainty in geometric classification of the points. We then determine the homogeneity of semantic classes for each point. The ratio of neighbors of a point in the same class as the point itself gives the data-dependent uncertainty. That is a measure of semantic uncertainty. We compute local geometric descriptors using covariances. We infer the shape of the local neighborhood using the eigenvalue decomposition of the local descriptors. We then extract multiscale features from these descriptors. These features are extracted using two aggregation strategies. Firstly, by aggregating features across scales by averaging, and secondly by computing the optimal scale where the entropy is minimum and then extracting features at the optimal scale. Now we feed the selected features including the saliency maps into a random forest classifier. To isolate the effect of aleatoric uncertainty, we run an ensemble of experiments with the presence of different intervals of these metrics in the training model. We then check which intervals of these metrics would provide the best accuracy. We take two regions from the Wahingen site provided in the ISPRS benchmark dataset. Area 2 has 0.27 million points with high-rise buildings and Area 3 has 0.32 million points with small independent houses. We obtained better accuracy when training with Area 2 and testing on Area 3 than vice versa. Hence, we train with Area 2 and test on Area 3 for the ensemble. Our results show that the features aggregated using multiple scales show higher accuracy in classification compared to those with the optimal scale. Points with entropy 0.5 to 0.8 are required for training using a random forest classifier, thus indicating mid-level entropy is required in the training set for improving accuracy. Points with semantic homogeneity has a wider range requirement. All sub-intervals of 0.1 to 0.8 are needed in the training data for using a random forest classifier. This indicates that both class boundary and object interior points are equally needed for improving accuracy. In all, we conclude that our proposed metrics of saliency map based Shannon entropy and semantic homogeneity determine the uncertainty in the data, which manifests itself in the accuracy of a learning algorithm such as the random forest classifier for specifically the task of semantic classification. Thank you for your attention.